So guys, hello again, and let's continue. I know that we have some questions in Telegram chat that Oleg promised to answer now. So let's start with the questions and then let's continue the workshop. Oleg?
Right, I'm back. Hi, very nice to see all of you again. Like, I hope nobody dropped. Very good, very good. Let's continue. Can somebody please voice the question, because I lost it.
Well, there was a question about aspect-oriented programming for Graal native image. Is CGLib or aspect-J support already in Graal native image or not?
All right, right. Yeah, this is an interesting question. And to answer this, we need to understand that the premise of the native image, how it works, right? All the classes, all the bytecode that will ever be executed has to be seen at the build time, right? So if you want to instrument something with aspect-oriented programming using aspect-J or some other library, right, you need to do that before you run it and feed it to the native image. At the latest, you can do this during the build time, right? So you can, there is an API to hook into the build process, and you can receive some events, like something about like what before analysis or after analysis, and you can maybe instrument your aspect points then, absolutely the latest, right? You cannot instrument code, or you cannot introduce new bytecode while the native image is running. So the compile time support is there, absolutely. The load time weaving supposedly also could work, but I think CGLib precisely is using something that is not very well working with the current implementation of the native image. There is definitely an issue about CGLib on GitHub, and that would be the best source of information about that. So instrument your aspects at compile time. That's a simple recipe. Right, do you have any more questions? I hope this answers. This is not the best answer, but this is the current answer.
Anyways, we can cover this in details during the session after the workshop, but so far we don't have any questions.
Let's continue. Right, let's continue. Let's continue. And at the very end of the last session, of the last part, we compressed our executable from 70 megabytes to 20 megabytes, which was still like not very impressive, right? It's megabytes, not just kilobytes, but it's a fully featured application, and it's runnable, right? So I can run this. It starts fast. It's all good. It's the same application. It does trade the size for the startup a little bit when you compress it with UPX, but if you need to do that, you can absolutely do that, and it will work. Let's go further, right? So we looked at the smaller deployment options, and a big part of that was to create a web application that we can turn into native image, right? So now it's the right time to ask, how can we deploy those native images, right? Because we know how we deploy our Java applications, and this is very simple, right? We throw the jar file into like a Docker container or something where we have the Java installed, and then we do Java -jar our file. Very easy. Can we do that with native image? Of course, we can use the same Docker image that it contains your operating system, your Java installed and everything, and just put the executable in there and run it. But this might be not the most efficient, right? Because the native image in itself, look, it just could be 20 megabytes, right? Doesn't need the JDK. So we can maybe save some space and make our images, Docker images, smaller, which will be very efficient at the deployment time, right? So in this section, we're going to explore one interesting, or maybe two interesting options, how we can run this application in Docker, right? So this particular tutorial here, the instructions, assume that you're building your native image in a Linux environment because it builds the image like I have here, right? So this, like if I do file this, file this, right? It's an ELF executable. So it runs, it's a Linux executable. So I can put it in a Docker container into another Linux and it will run. If you're building this application using a Mac OS, it will produce you a Mac OS executable. If you put that into a Docker container directly following the instructions here, it will not run because Mac OS executables cannot be run in Linux. It would be ideal if they could, but life is such that they cannot. So yeah, so if you build those, like if you want to actually follow the instructions here word by word, just build it in a Docker container first, and then so do this GraalVM native image from within the container, and then you'll get a Linux executable. Right. So let's continue.
Quick question. Any support for cross compilation?
Yeah, that'd be excellent. And I think we have been working a little bit on this, but I don't know the progress, and I don't think it's actually available. I know that there were some effort into making native image work better for the mobile devices, right? And that was improved recently, but I don't think there is a cross compilation support, as in you can build native images for Linux, say inside macOS. Maybe technically we could do that later, but there is no timeline. But it would be a very welcome addition because people have been asking for that for quite some time. Right, you can find an issue on GitHub definitely about cross compilation, and you can sum it up and maybe tell how important it is to you. But currently, it's specifically I'm not sure if I mentioned this or explained this before, right? Some native code from the JDK class library gets into the native image, right? So in that code is absolutely platform specific. So that is at least one of the reasons why it cannot currently, technical limitation, why it cannot cross compile, right? Because it uses the native implementation of the methods from the JDK that is platform specific. Probably we could resolve that in some way, but that is for the future. Right. So let's see what we got here. We have built the app and we built the native image out of the app. And I will not use the UPX app because I don't want it. I don't need to save those 20 megabytes or like 50 megabytes of space. Yeah, it runs, it starts, it's beautiful. I have my project built. Let's put it into the Docker image, right? We will use the following Docker file, and it's going to be very simple, right? We will use the operating system, and I will use the Oracle Linux Slim, Oracle Linux 8, but you can use any Linux that you would like. All I need to do is to put my application into that container and specify this application as an entry point. And then I will build it, right? So what I will do the dockerfileslim, and I will put those 3 lines in there. This is a striking contrast to what I would usually need to do for the Java application, where I would have the entry point pointing to Java, running that. So there is this additional level of indirection because the application is self-contained. I will build my application, build my Docker here. So I will just say, this is my file, this is my tag. So primes web slim. And the context, it runs, it builds, copies and builds. And then I will explore this image, this Docker image, right? So to do that, I would use the dive utility. It's kind of interesting. And what it gives me, it will give me some input, what my Docker image represents, what's inside that. So it fetches the image and it tells me that I have the 100 megabyte layer the from, and I just have my 77 megabyte large file, this application. Right? You can see the contents here. You can see the full, right? You can see the full thing. So image efficiency score here is 100%. This image doesn't contain anything that is not needed to be there. Where this is usually very important, this is very good for, example, for security. Right? The less stuff you have in your Docker image, the less stuff can be vulnerable to random security issues. Right? So if you have there a minimal operating system and just your application, it is better than having other things as well, because what's not there cannot be vulnerable. Right? So this is a 200 megabyte Docker image, and what I can do, I can of course run it. Right? And you can see that inside Docker, it starts just as fast. Right? So it starts under 100 milliseconds. And I'm using this 100 milliseconds as a very liberal threshold, because this is what typically your serverless frameworks will charge you by, right? So they will give you some compute resources, and how much you use that, you will be charged by like 100 millisecond step, depending on how much resources you use. So if you start under 100 milliseconds, and if you can serve something under 100 milliseconds, doesn't matter if this is like 2 milliseconds or 10 milliseconds, right? You will be charged the same amount of money. So at least from the economic point of view, that is not the issue. Of course, lower is better because this is time, but there is diminishing returns. So this is how you normally would package your applications, your native image applications. You will put them in the containers with just the Slim operating system, right? So let me put this back up so you see that in the middle of the screen. Right? In the middle of the screen. Right. Can we do better? Can we do better? Apparently, we can. Right? And one thing what we can do there is we can build a native image, and we can link everything statically into that, and only leave the dynamic libc linkage. Right? So if we do LDD build native image application, if we look what it links against, right? There are, for example, some libraries that can be linked statically, like for example, the C++ this thing, right? How do I do that? I just specify this command line option. How do I configure my native image build? When I use Micronaut, I edit the Gradle file. Build Gradle file, right? Build Gradle file. And this is very simple. So I will go here under the Micronaut, and I will just put this native image part here. Very simple. And I will build the native image again. A pro tip: if you need to reverse search for Gradle W, LEW works like a charm. I haven't found any commands where LEW come in the same sequence, only in the Gradle tasks. So my reverse search history is almost universally using this left thing. Magnificent.
Okay, while it's building, there is a quick question from the chat, and the question actually is about whether Alpine Linux will work instead of Oracle Linux.
Yes, that is a very good question. And Alpine Linux. So first of all, there is the upcoming support for Alpine Linux into the OpenJDK, right? I think to run in the Alpine Linux naturally, so to speak. As far as I know, people usually, for things like deploying OpenJDK-based applications into Alpine Linux, people usually use this Alpine Linux where you have additionally glibc, because normally your native applications will require glibc. So you use this Docker image from a certain Vlad on Docker Hub, fro Vlad or something, alpine glibc, and then you would put your application in there. And you can use that for native image as well, right? Well, it works in there, right? So can you use it or not depends on your particular conditions and whether you require support or anything like that, but it works there, right? So you just use the one with glibc available, and it will work. So it will be smaller. However, I personally don't think that is the best way to kind of decrease the size of the Docker image. And for example, this particular build that we're doing will also decrease the size, but will not use this kind of a combination of Alpine-based Linux and the glibc added on top of it, right? So what we've built now, we've built the native image, right? That is, wait a second, I need to move this zoom thing somewhere away, right? We've built the native image of with the libraries statically linked except libc, right? So we have the static executable with dynamic libc, right? So now you can see in the output of LDD here that we do not, for example, depend on the C++ thing, right? So this is only the libc that is a dependency, right? Everything else is linked statically. What we can do now with this, we can now build the Docker image that depends on the very minimal parent image, for example, distroless. So distroless is a project. Distroless is a project to provide minimal Docker images, right? I didn't want to open this, but you can Google for that. Distroless on GitHub, right? So we will use this very small base image that has the bare minimal things, right? So it has the certificates and it has some time zone data and it has something else, like a few files there, right? But it doesn't contain the full operating system. And it also contains the libc. It brings the libc with it, right? And then we'll use the Docker image based on the distroless base and just put the app in there. So let's see how it works. I think it should be smaller. I don't remember, but I think it should be smaller, right? So we will do Dockerfile distroless, right? And we'll just do those things, right? So see how easy it is to create Docker files for native image applications. It's beautiful, right? We've built this file and we need to build this image, right? We need to build this image. And now this would work, right? Because we are building, again, we are building on Linux, and then we are putting that into another Linux, which is very simple, right? So we took the distroless, we put the application in there, and we tagged it with distroless, right? Let's explore this. The previous one was something like, what was that? Almost 200 megabytes, right? So I assume this would be less than 100. How do I do that? I do dive and image, right? And if we look at this, yes, so the total image size is the 94 megabytes, I'm sorry, and 77, you need to remember, 77 is our application, right? So the overhead of the image is 16 megabytes. I think this is very comparable to the Alpine Docker images, specifically if you need to add the glibc in there. So if you would like to limit the Docker image size, I would definitely try to do this rather than the other thing, right? Rather than going with Alpine, right? And then if you want even more, right? Like, let me show you that it runs, right? Let me show you that it runs. I will run it the same way, and it runs the same way, and I can still access that in the application here. Sorry, my internet. Sorry about that. Right? we can still see that we are running it, right? And it works. And if I stop this Docker image, right, you can see that it doesn't work. So there is no trickery involved, right? What you can do even more, right? You can build a fully statically linked native images that use muscle C for the libc implementation, right? And that would be a standalone binary, right? And that binary you will use in a Docker container from scratch, and you will just put only the binary in there, and you will put it at the entry point, and that Docker image will be just the binary, right? From scratch is a totally empty Docker image. So it's very hard to be more efficient than that, right? You probably still need some things like the certificates, and maybe you need some things like the certificates actually baked in, but like time zone data and maybe some other things. But if you can pull it off, it is a very efficient and very effective way of deploying your applications. So this is the exercise that if you want, you can explore. The static binary, building static binaries works on Linux. It doesn't work on macOS, like in general, like macOS doesn't allow that. So this is something that you need to explore in Linux. And you can try this, but we will not do that now, right? So we have our distroless and we have our slim Oracle Linux-based Docker images, and we will look how to run our native images further. So let's go and check the configuring memory used by GraalVM native image. That is the next step. Do we have any questions, Timur?
No questions so far.
Excellent. What's your favorite way to deploy? Like, so I showed you 3 things. I talked about 3 things, right? Slim Docker images, distroless Docker images, and the from scratch native images. What would be your pick?
Well, from scratch looks very promising, but of course there are some limitations. One of them you've already mentioned, but well, what looks really impressive is from scratch.
Yeah, yes, it does. It is very impressive. Right. So let's check how we can configure memory used at runtime by the native images. And this is a very important topic, right? Because one of the main usages for GraalVM native images is to limit the amount of resource consumption that your applications, limit the resource consumption by your applications, at which GraalVM native image usually does a good job, right? But you also need to understand that you can and should configure memory used by native image. So let's do this. We're going to use the same web application that we talked before, and we've built the native image for a few times now. So we are not going to do that. How you can control the memory? You can use the same parameters that you would use for hotspot, right? So not all options that you can use for hotspot will be applicable to the native image, right? But native image does run with the GC, so it uses the managed memory, and you can configure the heap sizes. So let me just run the application and show you what I mean. So I will run my application here, right? And I will use the utility, and it's not in the instructions, but I just, because the instructions are Docker based, and if you're following those, you're good, and you can just see it that way. But I just wanted to show you this PS record utility as well, and show the memory usage. So if I do pgrep application, right, I just want to application, this is fine, right? And then I would like to do the PS record, right, help. What was the thing? I need the plot, right? I need the plot file, and what is the process ID or command? PS record /plot file process ID. So PS record /plot output PNG, right? And then the process ID, which was 8500. Right? So we are attaching to that process. We're attaching to the process, and we're gonna look at this file later, right? And now we're gonna execute some load on this application, right? So I will do that manually because why not? Where was that? Right, this one. So I will execute a few requests here. I will execute a bunch requests here, and we can see those the lists that it creates contain a few numbers. Right? And we need to remember that for every prime number we create, like the code implementation is not the most efficient, right? It was using Streams API that will create some objects on left and right. So it's supposed to run and use some memory, right? And then what we're gonna stop this, right? We stop this application. The PS record now I think output the plot, right? Output PNG. And then I will do the Python thing. No, simple. No, Python. HTTP. No, I will Google for it. Python server. Right. Python server. There was a one-liner to implement the server. Right? Somewhere here. Right, like this. Because I'm running in the cloud machine, so this is just Python server. Right. Right, maybe this one. Right. Wait, never remember the command. Python server. I just want to show you a picture. One line. Right. Right. I'm being stupid or what? Python server. No module HTTP. What am I missing? One liner. Oh, maybe like, yeah, large letters. Yes, of course. Yeah, like this. Oh, thank God. Right, this will work. Excellent. And all I wanted to do is show you a number, show you an image. Right, 8,000, very good. And then what we have the output PNG. Oh, yes. Right, so this is what we see. We were running our application here for a few seconds, like for 50 seconds, right? We did some requests. The memory grew up to 100 megabytes, and then we stopped. And the CPU was only used like a few times where I actually hit the requests, right? So if I would do a more thorough benchmark here, right? So I will do the same, but I will generate the, let me start this again, right? And I will use the load generator tool, right? To run for some time, let's say like 30 seconds, right? So I don't want load generator tool. I need the PS record, right? PS record, right? pgrep application, PS record, plot 9590, right? So we PS record this, and then we do hey, and then we do hey. Wait. We do hey for some time, right? We don't have to wait for the whole 60 seconds there, but we can. right? So I just yeah.
Well, there is a question from chat about observability options. Can we track memory usage or something else, just like we used to do that in plain old Java with command line tools, JConsole, JIT maybe?
Yeah, that's a good question. So currently, I think the thing that prevents using those normal tools is that there is no JVM TI support for native images, right? There is no Java virtual machine tooling interface available in the native image. However, you can build the native image and allow the VM inspections, which will allow you to do the heap dumps, like for example, when it receives this threads signal, right? The interrupt and stuff like that. So you can have some options into the visibility. I think the allowing VM inspections for native images are currently the enterprise option, but that would work, right? So I think JMap or JHat or whatever will not work, at least currently. It could be technically probably feasible to do that, but one thing that we experience when we talk to people who deploy native images is that they very often just treat them as applications, as native applications, right? So they will put them into the containers and sometimes just monitor and take metrics on the container level. And you, of course, you can add libraries that do metrics, right? You can, for example, add the micrometer to that Micronaut application, and then you will get the metrics from the Micronaut through a library, and you can export them to like any source you want, like Prometheus, Grafana, and all your other systems. But for example, using the Java agents that instrument your code by themselves to send metrics to like software as a service providers for the monitoring solutions, that will not work out of the box for native images, right? And the command line tools will not work very well as well, at least currently, I think. Why is that so? Thomas might have a better explanation, but to my knowledge is because the JVM TI is not working under the closed world assumption. Right.
Okay. And what about JMX support in general?
Well, JMX is a complex thing, right? JMX consists of a number of things. You can define the mbeans or mbeans, right? And you can have and use the mbeans, and they can collect the metrics, right? And then there is this part where you connect from the outside, and then you read the metrics from those beans from the outside, right? So you kind of invasively start reading them. Mm-hmm. That part of using JMX doesn't work as far as I know, right? The part where you define the beans and they provide the metrics, and you can use those metrics to do something useful, or you can use those metrics to export them from the application itself. That part definitely works, right? So the part that connects from the outside and triggers some like arbitrary code execution, that part is limited, right?
Well,
that is the JMX story.
Yes, well, in that case, one can use a workaround, for example, to make another endpoint and expose metrics with HTTP or something else, some other protocol that is suitable for them.
Yes, so for example, I think that the Micronaut micrometer, wait, this is a project. I wanted to open the documentation here. So micrometer is exactly that approach, right? You add the micrometer library for the metrics, right? And then you either can export the endpoint for the metrics, right? And you can hit them and get the data, or you register like a reporter, so to speak, and that reporter can send your metrics to like a number of to whoever you want here, right? So that's the way you would add metrics to your native image application. And this, of course, works in the native image mode as well, right? So if you want to export that to New Relic, you add the library and you say like, oh, please send my metrics to New Relic, rather than you deploy your application and then after the fact you say like, oh, I would like to actually monitor that. Let me hook in and make random code transformations and make my production application execute some code that didn't exist during the deployment step. Right, so that was that. Let me just close the applications here because I wanted to show you the memory usage, right? I wanted to show you the memory usage for this whole thing. So our PS record commenced, and if now I need to do, let me just open another tab here. I just need to remember this Python thing. Right, I will just open another tab for and connect to the same machine, just for the Python thing, right? Which is the spectacular. Wait. What was the CD Micronaut example? Right, and here we do Python, and here we just refresh this page, right? Right, so this is a different graph, right? So now we applied load to our application quite a bit, right? We hit it with a ton of requests. We can see a ton of CPU working. So we run it for like a minute. And then it used 800 megabytes of RAM, which is not a small amount of RAM. But the thing is, this is a very powerful machine, right? So this machine had like what? 100 gigabyte of RAM, right? 100 gigabyte of RAM. So if we just do not constrain the memory, it can use it all. So how do we constrain the memory? We do XMX. And we say like, oh, I want to run within the 64 megabyte limit with the heap of 64 megabytes. And then it runs the same way, and you can access your application the same way. Right here. Okay, yes, right. I can access it the same way, and I can maybe let's do the same pgrep application, right? And then we do the PS record, this thing, PNG, our number, right? So we attach the PS record, and let's do a very quick, hey, we don't even need 60 seconds, right? We can just do like 15 seconds because there is no warm up, so it should be fine. So it should be fine. We run this for 15 seconds, and then we need to stop this. I'm sure there is a memory allocation problems at this size maybe. But yeah, so we got some responses at the end of file. Doesn't matter, we just want to show the memory usage, right? So we stop the application now. And what we see, if we refresh this, our magnificent file here, we can see that it actually runs with the smaller amount of memory. There is an overhead because the GC implementation takes an overhead for the serial GC. It's the amount of could be like it needs to copy the survivor spaces. So the amount of memory total runtime usage could be larger, and because of the direct memory usage, it also could be larger. But you can definitely contain that. Right? So those are the command line options that you need to know. XMX, you can also specify the maximum heap size percentage. And if you want to look at the GC, you can always do print GC and verbose GC. And this is just an example here. I want to run this. Wait, yeah, I want to run this, and I will scroll up because here is the default heap policy parameters that you can see by default, right? So we said that we want a 32 megabyte heap. So it said like, this is my heap size, and the young generation size is, for example, only 3 megabytes. So maybe you want to increase that as well, right? And then you, of course, can look at the GC logs and see whether your GC algorithm is great or not. So that is how you control the memory used by the GraalVM native image. So very often I see people make this mistake when they run native image without any constraints on a powerful machine, hit it with the load, and then kind of say like, oh, it still uses like a gigabyte of heap or a gigabyte of RAM. Well, of course it uses, because you give it all the resources in the world. The only thing that constrains it are the heuristics, and it runs, right? I am actually rambling about this a little bit too much, so we need to continue. I just saw the clock, right? So we will not explore the GC options, but we will go immediately into the profile guided optimization section. If you're doing this at home, the GC options allows you to specify the G1 GC for the native images. This is an enterprise GraalVM enterprise feature, but I think it currently only supports Linux as well. So not on Linux doesn't make sense to do that lab. So for the sake of saving time, we just go straight to the profile guided optimizations, because this is a way more interesting topic, right? So profile guided optimizations is the way to increase the performance, the throughput of native images. How it works: when we run with the JIT has the visibility into the code that runs. It can look at the profile of the workload. It can look at what code is executed and which code branches are taken, right? It can speculate and then compile using the certain profile. So ahead of time compilation cannot speculate, because it cannot de-optimize and compile again, at least in the current implementation of the native image technology. But what it can do, you can build an instrumented image that will record the profile for you, that will gather the profile, and then what it will do, it will use that profile when you build the final native image. So it's a two-step process. And we're going to do this. We're going to use the same artifact that we're still using, right? Our Primes web application. But what I want to do is, in the previous lab, we wanted to run this. Look, I wanted to run this. So I will run this Docker image, but I will do the slim, right? We just use this. This is our Primes web slim image, right? Is the normal native image put into the Oracle Linux slim environment, and we run this, and give it the memory limits. For memory, we disable the swap and say one CPU only, right? So we run this, and then we apply our Hey. Hey is a load generating tool. Let's say like we want like 30 seconds. 30 seconds. So it now starts hitting our application there. And while we are doing this, I want to go to the C advisor running on my machine there. C advisor is of course a monitoring tool, and I will open the stats for our Docker container. I just want to see how they load and some graphs, right? So we can see that the limits are in place. We can see that our CPU uses like one CPU. We can see that all the cores on the machine can be used there. And what's important, we see the memory is under the 200 megabytes. Under 200 megabytes. So this is how you can monitor the performance of your application and how much memory, for example, it takes. You just do that on the container level, right? So here's the number that we need to record. It is, so we threw as many requests as we could on this without any disregard for the latency and response times. And we run it for 30 seconds. And our distribution response time histogram is a little bit like this. Not very precise, You can increase the granularity using hey later, but this is the important number that we want, is the request per second, the throughput of our image, right, of our application was this, which might be good or might not be good. This is our baseline, right? Like it doesn't compare to anything. I will put it into some here, right? So this was a normal serial GC default native image, 256M, 1 CPU, right? Just to save it, right? So now we're gonna build the profile guided optimizations into the native image. How we do that? Very simple. We edit our Gradle script here, build Gradle, of course, right? And we find the native image section, and we delete this, and we do args. I'll copy the line. I'll copy the line, right? So PGO instrument. Well, we can also enable the G1 GC. I don't think it does. It makes the most, like, let's do the PGO, just the PGO, right? Let's do the PGO. Let's do the PGO. This is the whole line, right? PGO instrument, done. We save this. We do the build, right? We do the build. Now, in this section, there will be a little bit of building. So, because we need to build the instrumented image, and then we need to build the final image, and then we need to run the test again. So if you have questions, now is a good time. Thomas, do you have questions?
No questions so far.
Yeah, it's good. Very good, Oleg.
Very good that we have still have you with us, right? No, PGO is one of the great things here, right? Because why is this? Because it can give us the profile, and Thomas can speak about that in more detail. But for example, if you have the workload that heavily features, for example, one branch in a certain conditional, right? The profile can kind of skew the distribution of the options there very heavily, right? Maybe you always go into, like, there is a null check and you never get nulls, right? Using the profile, you can maybe output a better optimized code for that particular check, knowing that you almost never get nulls, right? So, and this, like, just the simplicity of this example should tell you, and you should recognize that pattern, checking for nulls, for example, right? And you understand that that code is everywhere, right? So if you can optimize better those very common idioms, that means you can optimize much better.
Yeah, and in general, I mean, the profiles also tell you which parts of the application are important, meaning they're executed more often. And then we will spend more compilation budget in terms of compilation time and more machine code on the parts that are common in the program. So this having a profile for a program has a huge effect. Not just, null check is a very good example, but it's just one of the things. There's almost every optimization is one way or another consuming the probabilities along all the paths of the program.
Yeah. Do you remember the data, right? When we started building the GraalVM compiler as a native image, as a shared library, I think initially we didn't do it with PGO, and then we turned on the PGO. Do you remember if that had any noticeable effect?
I think it was about 20%, almost 20% better throughput for our compilations.
Right. Yeah. So 20% is quite a bit, right? If it could be the difference between, like, fast and very fast.
Yeah, no,
right.
I mean, and 20% for free is for sure good.
Absolutely. Right. So our application is done here, right? So now we have the binary. Now we need to build the Docker image for this binary, right? Because we don't need to build the Docker image for this binary. We need to run it. I'm running in front of myself. We run, and this is the instrumented binary, right? This binary contains the code that will output the profile. So we're gonna hay over it. Let's say the same 30 seconds, doesn't matter how much time, like half a minute spent, right? So while now our application here gather profile, right? Profile, and hopefully it outputs it to the key, which is the default iprof file, right? While it runs, we'll continue further with the instructions here, right? So we see that there is the file, and what we need to do now, we need to say that, oh, I want to use the profile guided options and give the path to file. Double dot nonsense here is because Gradle plugin here builds into like a built native image directory, and the profile will be, well, in the folder where we run, right? So here, did we do it? Yeah, it's done. It's done. So we can stop this, right? We stop this, right? And the profile file default, right? It's there. How big is it? You're asking. I hear you asking how big is the profile file. It's 12 megabytes. Fine. So let's do the second build further, and then and then we'll talk further about this. So we need to change this. We need to change this, right? We have too many parentheses here. Right. Default iprof, and let's not the G1 GC because we didn't do that, right? We just use the PGO, right? We save this, and now we do the left thing again and build the native image again, right? So this process seems tedious, but it's actually very natural. You execute tests, you execute your benchmarks, you execute, and you probably do that in your CI. So your CI probably can build the native image, apply the load, generate some tests, generate some profile, and build the native image without you even noticing that it actually did more work than just building the native image once. Right. So we're going to build this native image now, and this will be the instrumented.
Excuse me for interruption. What happens if the workload changes? Well, when you are building your native image based on some profile that was actual for some specific circumstances, and what if those circumstances are not actual anymore?
Yes, yeah. I can answer that.
Yeah, Thomas, go ahead, please.
So the profile is very approximate. So even if your circumstances change, it shouldn't affect, like the profile doesn't need to be very precise. It can be really super approximate. And the worst case scenario is that, like, well, you trained it on scenario A, and then let's say scenario A doesn't happen at all, and it's always scenario B, then maybe your performance is not improved. But the performance would not be worse than without profile. And in most cases, like even if your behavior of your application changes, the usage of some of the core libraries and core functionality of your app stays the same. And the profile has to be only very approximate to be useful. So I think it should be very rare that it's really a very negative impact. And the worst case scenario is that you just don't get the speed up.
Well, it's very important clarification because it's unlike it is done in JIT that is in hotspot, because when some code de-optimized, it falls back to the interpreter mode, and interpreter mode is much slower than when your code runs in compiled mode. And well, if you have two options, just the default option and more optimized option, then it's much better.
Yeah, the difference is not as big. It's only 20–30% difference in performance that you would gain or lose. And so there is not that big of a performance cliff, even if the profile is not mentioned.
Right, thanks for the answers. Our application has built in the meantime, and I will use the same Slim Docker file because that's the normal Docker file that we used, right? Copy the application in there, and we will tag it differently because now it will have the optimized application running there. And I will execute the same test again, right? I will now run this PGO thing. I will run the PGO thing. It runs. Let me check if it runs. Yeah, it runs. Very cool. And now we're gonna do the benchmark. Did we run it for 30? Not that much because there is no. Last time we had what? Had 3,500%. Let's see if PGO makes any difference. Drum roll. Any audio effects in the production? Probably not. Probably not necessary. Let's just wait for a couple of minutes, and then we see whether it improves. Right. So what we have now, we have 5,300 requests per second. This is the PGO at work, right? So if we do what? We do this, and before we had what? 35. Let's check that, right? This divided by 35, 46. That's what, like 50% increase. That's 50% faster than before. With the same limits that we had, because we run the Docker container right here with the same memory limits, right? So this is the effect of the PGO, which is absolutely excellent, right? Absolutely excellent. We can add G1GC on top of that. That doesn't. It's not the most important, right? If you want even better performance, if you are like, I don't care about the memory usage, right? I do care about the memory usage, but my main thing that I worry about is the peak performance. The very simple answer is you should use the JIT. Right? The JIT has the best visibility into the system. The JIT is adaptive for your workloads. So using GraalVM JIT will probably give you better results. Not necessarily if you actually divide that by the amount of memory used and if you limit the CPU, but like if you can run it in a more powerful machines without any second thought, then the JIT is what you want. Let's do that. Shall we do that? Shall we do that? Shall we do that? It's actually very simple. This lab is very simple. The only notion here that is important here in this lab is that there is the warm-up, right? The warm-up is there, so we need to take that into account. Right? We have built this application before. Let me just clear the screen, right? So I do have the jar file there in the build libs primes something all, right? This is my jar file. I can run it again. My Java minus version is Java 11 GraalVM, so I can do Java minus jar and this thing. And we are not constraining this like any resources here, right? We just run it locally. There is no Docker interface. There is like, if we probably hit this through localhost, this will be faster than going through the Docker. Sorry about this. but it could be faster, but we just want to see the largest number that we can. And this is very simple, right? We're going to use the same hey utility here. Hey, hey, hey. And we're going to warm it up for 3 minutes. We're going to warm it up for 3 minutes. I'm not sure why 3 minutes. Probably could be just as good with fewer minutes. But we're going to run it, and then we're going to do the benchmark, and then we're not going to compare it to anything. The instructions here tell you that maybe you want to compare it to some other JDK if you have that available on your machine. But it's a little bit boring wait, because you need to run the same like for 4 minutes, because you need to warm it up, and you cannot just run it for like 30 seconds. So it's not the most interesting entertainment in the world. I would recommend you to do this, right? And because you're running this in the same environment, using the same resource constraints, so it just like the only thing that is different is the Java implementation. You can compare those two measurements, and you can tell us which was faster. Right. So let's look at this. I know that there were some people who wanted to talk about the GraalVM JIT, because I saw those questions when we're going to talk about JIT in the channel before. So now is the good time to talk about JIT.
Probably they meant JIT that is that can be plugged to the Java compiler interface, not for native image, but for classic Java.
Yeah, but this is not the native image, right? This is our classic Java. This is hotspot. This is Java hotspot virtual machine, right? When I do this Java minus version, right? And when I do this Java minus jar something something, this is the hotspot running. There is nothing about native image here. This is the pure hotspot with the top tier optimizing JIT compiler being the GraalVM compiler, and then it integrates with hotspot using JVM CI. And yeah, this is the JIT. This is the JIT. That's why we need to actually have the warm up, because for the native image, we don't need the warm up. And for the JIT, we do, because initially the code is interpreted, and then it goes through the compilation phases, through the tiers of compilation, and then it hits the top tier JIT, and then the better JIT produces better machine code.
Yep, actually a year ago I can remember that there was a nice talk about comparison of C2 compiler and GraalVM JIT compiler, and well, in some cases GraalVM compiler outperformed C2, and well, I guess that since that moment a lot have changed, and there are more improvements to GraalVM JIT compiler, and well, probably you can give us some update notes about this.
Yes, so we improved the GraalVM JIT compiler both on the Community Edition and on the Enterprise Edition. And as far as I remember, the talk, I think, was only comparing the Community Edition against C2. It was not comparing the Enterprise Edition. So we think the Enterprise Edition should, in almost every scenario, be better. We're treating a scenario where we're not better as a bug in the team, basically. And in terms of the kinds of improvements we made, is on the Community Edition, I think most notably we added some range check elimination algorithm that we merged from a community contribution. So this is specifically improving the performance for code with bounce checks. Yeah, on the Enterprise Edition, we did, various improvements, but it's probably too many to enumerate them. Yeah, you can see our enterprise edition performance improvements on the release notes of 23. We continue to push the performance barrier. I think we're still not at the point where we say, oh, performance is done. There's always a few more percentages to gain, and with so many Java workloads out there, having a faster Java execution is actually good for reducing usage of CPU cycles, like almost worldwide.
Yeah, if I might add, if I remember that session correctly, it didn't only include the GraalVM Community Edition, but it only included the version of the GraalVM compiler that was included in the OpenJDK, right? Which is for 11. I don't think that was updated anytime recently, because OpenJDK 11 pulled the GraalVM sources quite some time ago when the 11 was stabilizing, I think. So,
in general, we just encourage anybody to use Enterprise Edition to test it on a workload, and we see very good results with Enterprise Edition, and we're curious to hear from you guys if you can replicate that. But we are very confident that this would replicate on your workload.
Right. So this benchmark finished, right? We see order of magnitude different numbers here, mostly because this was an unconstrained execution of the Java process, so neither by CPU nor by memory. So it could allocate as much as it wanted, and it could use all the parallelism in the world, like on this machine, sorry, not in the world, to process those requests. But this is a very simple way to kind of assess the performance. You just hit a couple of URLs for your particular workloads. And as Thomas mentioned, right, there is no substitute for evaluating GraalVM on your workloads, right? So, and this goes both for the performance of the JIT compiler and for the performance of the native image executables, right? Because your code is special, right? Your code is yours. You should run it with the JIT and see whether it improves performance and by how much. And then you also can try, for the new project specifically, you can try running them and consider deploying them as native images if you think the use cases for that are relevant for you, right? So memory consumption savings and the startup improvements, if those are interesting for you, then you should definitely check out the native image. I think we have just 5 minutes left in the workshop. I'm bad with time. We have one more thing here, exploring the JIT. And this lab here, this particular task, is about looking into the internals of the GraalVM. So you can specify some debug options, right? And you can look at them in the docs. There are a bunch of them that you can specify to run. And for example, one of the interesting ones is you can dump the internal representation of your program. You can dump the compiler graphs, those CF node graphs, into a file, and then you can use software. You can use software to look at those files, right? And I will not actually run this benchmark again for you because it's the same code, but I will just show you how it looks. So you can download the ideal graph visualizer from the download page of the GraalVM, and then you can run it. You can run it like this, and you can see I have a bunch of them downloaded. So it runs. It's an application with a graphical user interface, and then what you do, you take the graph that was created by this Graal dump option, and you load into that application. one important bit there is for the graphs to actually be created, you need to actually make sure that your code reaches the top tier JIT, right? If the JIT doesn't see the graphs, right, it cannot dump the graphs. So you want to be sure that you run your application, right, and then you apply the load to make sure that the code that you're interested in how it optimizes, the code actually hits hits the JIT. And then you would find the files, you download the files, and you put them here, and it looks quite magical. I'm not sure how well this will work with the screen sharing and everything, but you will see some data on the left, which are the certain stages of how the code looks. And this particular graph here is for this one method, primes controller, prime sequence, the only method that we dumped the graph for, right? And you better have a large monitor to look at those because they can get quite large. But I just wanted to show you how it looks like. So they encode both the control flow and the data flow in the same graph, and you can sort of see the functionality of this. So initially the graph was created, it was quite large, and you can see that there were some logic here. There was the long stream filter because we are filtering the prime sequence, right? And there were some boxing happening, and then some collection and everything. It's a little bit small, right? The graph is smaller, but it's very abstract. So during the compilation, right, the graph gets larger but less abstract, and then it optimizes. It optimizes and optimizes, and there are some articles about how to read those, right? And we are not gonna spend a lot of time on those here, but this is something that the engineers on the team are doing when they're exploring the performance bottlenecks or any performance issues or potential optimizations. They look at how the compiler sees the graphs, and they make those transformations on the graphs, and then they run the benchmarks again, and then the transformations are good and the benchmarks show good results, and that code is shipped and it gets into the GraalVM distribution, and you download that and you enjoy better performance.
Oleg, it seems that it's time to wrap up our beautiful workshop. Yeah, that's right.
Yeah. It is time to wrap up. I don't think we have time for questions much here, and I will stop sharing my screen here as well. Maybe I will manage to turn on my camera and my internet will be good enough for me, so you can also look me in the face and type in chat how much you enjoyed all of this. Right. So this was our workshop. We will still have time for questions in the expert zone, right? In the discussion zone, right? But the instructions here will stay. So I welcome you to try it again, maybe at the later stage, maybe after the conference, where you have more time to dedicate to a single subject rather than trying to jump between the calls and conference sessions. And yeah, GraalVM is here to stay. The project is evolving, and thank you very much.
Thank you, guys.
Thanks.
Thank you for your
great
workshop. Yeah, and I hope to see you soon next conference. And yeah, see you.